Hello. Yeah, good afternoon, everybody. How are you guys? So, today we will continue with the further portion of application of derivatives. Before starting, I would like to know if my voice and video, if my voice is audible and video is visible to you. Please tell me. Give it a quick cross check. All right. Thank you so much. Maximum people, it is visible and I am audible also. Thank you. So in the last class, we did monotonicity. I am assuming that you must have tried certain questions on the monotonicity also. All right. So today we will start with maxima and minima. All right. Maxima and minima. So two kind of maxima we talk about: local maxima, local minima, global maxima. Similarly, two type of minima we talk about: local minima and global minima. Initially, what is the need? We should talk about local maxima and local minima. All right. So, local maxima is simply nothing. If the value of the function at that particular point is greater than its both the neighbors, like it is happening. Say this is the point x equals to a. This is the point x equals to a. In the right of it, this is x equals to a plus h. In the immediate left of it, this is x equals to a minus h. So if this f of a is greater than f of a plus h, as well as it is greater than f of a minus h. Am I clear? If this at x equals to a, value of the function is greater than f of a plus h as well as greater than f of a minus h. Means value at this point is greater than its both the neighbors. All right. Then x equals to a is called the point of local maxima, and f of a is called the point of local, is called the local maximum value, not the point, is called the local maximum value. All right. So if we go with the particular definition, see y equals to fx, a function defined at x equal to a, and also in the vicinity of x equals to a. Means function is defined at x equals to a as well as in the neighborhood of x equals to a. Then fx is said to have a local maximum at x equals to a if the value of the function at x equals to a is greater than the value of the function at the neighboring points of x equals to a. And those neighboring points are what? X equals to a plus h, x equals to a minus h. Am I clear? Mathematically, f of a is greater than f of a minus h and f of a is greater than f of a plus h, where h is positive and very small quantity. Now see, in this entire definition, I did not talk about the differentiability. Got it? Nothing comes in between that the function is differentiable or not differentiable. Now see, if the function is like this, and this is the point x equals to a. This is a maxima. Am I clear? If the graph of function is like this, even then x equals to a point of maxima. Am I clear? And above all, if the graph of the function is like this, but this is the value at x equals to a. Even then x equals to a is point of maxima. Do you realize this? It look like point of minima, but value at x equals to a is greater than its both the neighbors. Got it? So value at x equals to a is greater than its both the neighbors. Am I clear? So that is why we call it point of local maxima, and we call this value as the maximum value. All right. Now, similarly, it goes for minima. Minima, like value at x equals to a is lesser than its both the neighbors. Am I clear? Like the graph of the function is like this. This is x equals to a. This is x equals to a plus h. And this is x equals to a minus h. Am I clear? So now what is happening? F of a is less than f of a plus h, as well as f of a is less than f of a minus h. So value at x equals to a is lesser than its both the neighbors. So whenever this thing happens, that the value of the function at that point is less than its both the neighbors, this is what we call the local minima. Like here in the definition, if we see, fx is said to have local minima at x equals to a if the value of the function at x equals to a is less than the value of the function at the neighboring points of x equals to a. Mathematically, f of a is less than f of a minus h, and f of a is also less than f of a plus h, where h is more than 0. Am I clear? Here also same thing. There is no discussion about the continuity of the function. There is no discussion about the continuity or differentiability. If the graph of the function is like this, then this x equals to a is what? Point of minima. If the graph of function is like this, even then this x equals to a point of minima. Point of minima. If the graph of function is like this, you see value at x equals to a, this dark point is the value at x equals to a. It is less than a plus h as well as a minus h. Got it? So again, this x equals to a is point of minima. I hope everyone is clear about every one of you is clear about the point that wherever it is point of maxima and wherever it is point of minimum. Have a look. Got it? Is it fine, guys? Now, let's take an example. See, the graph of a function is something like this. Got it? Graph of a function is something like this. Now there are certain points. Say this is x equals to a. This point is x equals to b. This point is x equals to c. This is x equals to d. This is x equals to e. This is f. And this point is x equals to g. Now let us see at the individually at which point this function is increasing, at which points this function is decreasing, and whatever is happening. See, at x equals to a, what is happening? It's both the neighbors are both the neighbors are having lesser value than the value at x equals to a. So x equals to a is what? Point of maximum. Now, at x equals to b, what is happening? See, in the right of b, value is gone greater. If you see, in the right of b, value is going greater. In the left of b, value is also greater. Got it? So this x equal to b is what? Point of minima. Now, at x equals to c, left value is lesser, right value is greater. Got it? Left value is going lesser, right value is going greater. So here function is increasing at x equals to c. Now come to x equals to d. At x equals to d, this is the value. But in the neighborhood of d, it is going up and the left also going up. So it is point of minima. Minima at x equals to d. Now, at x equals to e, what is happening? Left value is greater. Do you see that? Right value is lesser. Left value greater, right value goes lesser. So it is decreasing. Decreasing at x equals to e. At x equals to f, I don't have to say anything. It is clearly point of minima. And at x equals to z, again, I don't have to see anything. It is the point of maximum. All right. So this is how we judge about the maxima, minima, increasing and decreasing behavior of a function near a certain point. Am I clear? Now we will think of something, some few points, important points. Write down the term turning value or extremum value. Extremum value. So turning value or extremum value is used for both maxima and minima. Am I clear? The term turning value or extremum value, it's not off, it's on. Turning value or extremum value is used for both maxima and minima. Got it? Now, maximum and minimum values of a function, maximum and minimum values of a function may not be its greatest or least value. May not be its greatest or least value. Even at times, it may happen that a minimum value is greater than a maximum value, like this. Like this. This is minimum and this is maxima, and this minimum value is greater than this maximum value. Even a local minimum value can be greater than a local maximum value. Am I clear? Now see, if a function is continuous, what will happen? It may have this kind of graph. So what will happen? Maxima, minima, maxima, minima, maxima, minima, and so on. So if a function is continuous, these maximum and minimum will occur alternatively. We cannot have two maximas simultaneously or two minimas simultaneously. Between two maximas, there will be at least one minima, and between two minimas, there will be at least one maxima. Got it? For a continuous function, maximas and minima occurs alternatively. For a continuous function, maximas and minimas occur alternatively. Got it? Maximas and minimas occur alternatively. Right? And most important thing, if a function is non-derivable. See, if a function is derivable, we have ways to find maxima and minima. But if a function is non-derivable, then maxima and minima can be observed by graphs or by general analysis, or I should say analytical analysis. Am I clear? By general analysis. Now, so this is all about maxima and minima. Now, how do we check maxima and minima? So what we are saying here, if a function is differentiable at x equals to a and it has a critical point of the function x equals to a and it is the critical point of the function, then we have the following three tests to decide whether the function is having a maxima or not having a maxima. Got it? So mathematically, so if function is derivable or non-derivable, simply what do you see? Fa is less than f of a minus h. Fa is less than f of a plus h. Then x equals to a is minimum. Got it? So if a function is either it is derivable or it is non-derivable, this is a simple test. Now, there are two further tests. One is the first derivative test, other is second derivative test. First, we will go with first derivative test. Let me explain it to you. Say a function is like this. Now, at this point, say this is the point x equals to a. Now, you realize exactly at x equals to a, tangent is getting parallel to x-axis. At x equals to a, tangent is parallel to x-axis. Am I clear? Tangent is parallel to x-axis. So at this point, derivative is going to be 0. At this point, derivative is going to be 0. Now you see what is happening in the left of x equals to a. This function is increasing. So f dash a minus is positive. What is happening in the right of x equals to a? Then f dash a positive is going to be negative. In the left, it is positive, increasing. In the right, it is negative, decreasing. Got it? So, what is the first derivative test? First derivative test for maxima is fx would have a local maxima at x equals to a if f dash a minus is more than 0, like I told you, and f dash a plus is less than 0, like here I told you. It means f dash should change its sign from positive to negative. Am I clear? So it will be a point of local maxima, but definitely it is for the derivable functions. Now, let us assume a function is like this. This is x equals to a. Again, what is happening exactly at x equals to a? Tangent is getting parallel to x-axis. So f dash a will be 0. Now what is happening in the left of a? F dash a minus. This function is what? Decreasing. So derivative will be negative. F dash a plus. This function is what? Increasing. Derivative will be positive. So what is happening? Fx would have a local minima at x equals to a if f dash a minus is less than 0. Means function is decreasing before x equals to a, and f dash a plus is more than 0. Means function is increasing at in the right of x equals to a. That means f dash x would change its sign from negative to positive. Am I clear? Now, if fx does not change its sign while passing through x equals to a, then fx would have neither a maxima nor a minimum. That means here derivative is certainly 0, but function is either increasing or decreasing. It will be something like this. Like this. This is x equals to a. You see, at x equals to a, tangent is 0. But here also derivative positive, as well as here also derivative negative. Positive. All right. So let us give it a quick recall for the first derivative test. If at x equals to a, function derivative is 0, but before a, derivative is positive, after a, derivative is negative. Means function is going from increasing to decreasing. Increasing to decreasing means at x equals to a, it is the point of local maximum. Now, at x equals to a, derivative is 0, but before x equals to a, derivative is negative. After x equals to a, derivative is positive. Means function is going from decreasing to increasing. So going from decreasing to increasing means x equals to a is point of local minima. I hope I have made my point very clear. Now, let's go with an example of the first derivative test. See, fx is given as x plus 1 upon x. Discuss the maximum and minimum value of fx. All right. See, first of all, let us do f dash x. F dash x is 1 minus 1 upon x square. So this is basically x square minus 1 upon x square. Now, for maxima, minima, what do we do? F dash x should be 0. F dash x 0 means x square minus 1 upon x square should be 0. So x square is 1 means x equals to plus minus 1. Now, as of now, it is not guaranteed that 1 or minus 1 will be point of extremas. Function can be increasing at these points, that we will further check. Now, first of all, let's go with x equals to 1. F dash 1 plus. See, x square is going to be more than 1. X square minus 1 is going to be positive denominator is also positive. So f dash 1 plus is greater than 0. And f dash 1 minus. Now see, if we are at little less than 1, then value of x square will further decrease, will be less than 1. So x square minus 1 is going to be less than 0. So in that case, this is less than 0. Am I clear? So function is going from increasing to decreasing. Increasing to decreasing means x equals to 1 is point of maxima. X equals to 1 is point of maxima. In that case, maximum value will be the value at x equals to 1. That is 1 plus 1. That is 2. There is some problem. 1 minus 1 by x square. It is x square minus 1 upon x. Oh, no, I made a mistake. In the right function is basically increasing. In the right function is increasing. In the left function is decreasing. So it is going from decreasing to increasing like this. So in that case, x equals to 1 is point of minima. And minimum value will be what? F of 1, that is 1 plus 1, that is 2. Minimum value will be 2. Now let's check for x equals to minus 1. F of minus 1 minus, in the left of minus 1. Say left of minus 1 is minus 1.1. F dash. So minus 1.1 square is more than 1. So this numerator is going to be positive. So this is going to be greater than 0. Am I clear? And f dash minus 1 plus, in the right of minus 1, say it is 0.99. So 0.99 square will be something 0.98. Minus 1 you do, it will be negative. So it is going to be less than 0. So in the right of minus 1, function is decreasing. In the left of minus 1, function is increasing. So graph is going something like this. So if the graph is going something like this, means x equals to minus 1 is point of maxima. And maximum value f of minus 1 will be minus 2. Now, are you not surprised that the minimum value is greater than the maximum value? Minimum value is 2, whereas the maximum value is minus 2. Basically, the graph of this function goes like this. Like this. This is the graph of this function. This is x equals to 1. This point is 1, 2. All right. This point is 1, 2. It is the point of maximum. And this point is minus 1. This is minus 1, minus 2. And this is the point of minimum. Am I clear? So this is how it works. Now let's do another question before proceeding further. So the question is y equals to ax plus b upon x minus 1, x minus 4 has turning point at p 2, 1. Then they're asking you to find a and b. Now, first of all, understand the question. This function has turning point at p 2, 1. So now two situations arises. First of all, this function is itself passing through 2, 1. And if it is having a turning point, means it is having a maxima or minima at this point. So at this point, derivative is going to be 0. Am I clear? So first situation is why this function itself passes through passes through 2 comma 1. Let's make it pass through. This implies 1 equals to 2a plus b upon 2 minus 1, 1, 2 minus 4, minus 2. So that means 2a plus b is minus 2. Got it? So one situation clear. 2a plus b is minus 2. Now second situation. If this 2 comma 1 is a turning point, that means dy by dx at x equals to 2 is actually 0. This should be something like this graph or like this graph. So here derivative is going to be 0. Now this y is I'm writing again. This is ax plus b upon x square minus 5x plus 4. So dy by dx is square of the denominator derivative of numerator a minus numerator derivative of denominator 2x minus 5. Got it? Now don't simplify it. Directly what you do, dy by dx at x equals to 2. Put directly x equals to 2. So we are going to get 8 minus 10 minus 2a minus 2a plus b into minus 1 upon may whatever it is 0. So this denominator will directly go to 0. So with this minus 2a plus 2a plus b is 0. See 2a cancel. That means b comes 0. Now if b is 0 and you have another relation 2a plus b is minus 2. 2a plus b is minus 2. You put b equal to 0. So 2a is minus 2. That means a is minus 1. So this is your answer, a minus 1, b 0. Am I clear? So this is how we utilize this information. Got it? Let's do another question. See, find the points of maxima and minima. Find the points of maxima and minima for fx equals to 12x to the power 5 minus 45x to the power 4 plus 40x cube plus 40. All right. Now, what do? We will differentiate it. Got it? So if you differentiate it, you get f dash x as 60x to the power 4 minus 180x cube plus 120x square. This is what you got as f dash x. Out of it, I take 60x square common. So you get x square minus 3x plus 2. So it is 60x square, x minus 1, x minus 2. Am I clear? Now, let's keep it as it is. Now, let us observe the behavior of this in the neighborhood of these points. Because if you do f dash x 0, you are going to get x square into x minus 1 into x minus 2 as 0. So, x is 0, 1 or 2. Am I clear? X is 0, 1 or 2 we got. Now, let's check it. F dash x at x equals to 0 positive. Now see carefully in the right of 0. 60 positive, x square positive, 0 minus 1 negative, 0 minus 2 negative. So ultimately this is going to be more than 0. Got it? And f dash x in the left of 0. Left of 0 means like take minus of 0.001. what will happen? Positive, positive, negative, negative. Ultimately, overall product is what? Positive. So now, see, in the neighborhood of x equals to 0, derivative is not changing its sign. In the neighborhood of x equals to 0, derivative is not changing its sign. It was increasing earlier. It is going increasing even later. So x equals to 0 is the point where function is increasing, because derivative is positive in both the neighborhood of x equals to 0. So function is increasing at this point. All right. Now f dash x at x equals to 1 positive. Now see, in the right of 1, 60 positive, x square positive, x minus 1 will come positive because you are in the right of 1. But x minus 2 will come negative. So it is overall less than 0. In the right of 1, it is negative. F dash x at x equals to 1 minus. Now in the left of 1, 60x square is certainly positive. X minus 1. Since you are in the left of 1, this is going to be negative and this is also negative. So overall product is what? Positive. So in the left of 1, function is increasing. In the right of 1, function is decreasing. Increasing to decreasing means like this. So x equals to 1 is point of maxima. X equals to 1 is point of maxima. Similarly, in the neighborhood of x equals to 2, if you check, in the left of 2, it is going to be negative. Just a moment. Left of 2, positive, x minus 1 will come negative, x minus 2 will also come negative. So in the left of 1, left of 2, function is, derivative is negative, and derivative is positive in the left of 2, positive. This is also positive, but this is negative. So derivative is negative, and f dash x in the right of 2. Now everything is positive, positive, positive. So it is positive. So function is going from decreasing to increasing. So x equals to 2 is point of minima. Am I clear? So x equals to 1 is point of maxima, x equals to 2 is point of minima, and x equals to 0 where derivative was 0, but function is not having any maxima minima. It is the point where function is increasing. All right. Now, this was all about first derivative test. Now, let's talk about the second derivative test. Now, what is happening? This test is basically the mathematical representation of the first derivative test. It simply says, now see, before second derivative test, let me tell you something about concavity. There is a word called concavity. Concavity. Got it? So concavity, there are two kinds of graphs we have, either this or this. This type of graph we call concave downward. This kind of graph we call concave downward. And then we have this kind of graph which we call concave upward. Got it? There are two kinds of graphs, concave downward like this kind of shape and concave upward like this kind of shape. All right. So wherever the graph is concave downward, second derivative goes less than 0. Wherever graph is concave downward, second derivative goes less than 0. And wherever graph is concave upward, second derivative goes positive. Concave upward, second derivative positive. Concave downward, second derivative negative. Now, what happens sometimes in the graph of a function, there comes a point where concavity changes. Like here, if you see, there is this point. This is the point. Say this point is x equals to a. Before x equals to a, you see it is concave downward. After x equals to a, you see it is concave upward. At x equals to a, concavity changes. At x equals to a, concavity changes. At x equals to a, there is a tangent which is cutting the graph. At x equals to a, there is a tangent which is cutting the graph. So this x equals to a is called point of inflection. This x equals to a is called point of inflection. Have a look at it for a moment. This x equals to a is called point of inflection. Got it? So basically, point of inflection is a point where the graph cuts the x-axis. This x equals to a is the point, this point of inflection is the point where tangent cuts the x-axis, means function is derivable. Now this derivable function, sometimes there is a possibility that it is not derivable. But the reason for being non-derivable is what? Reason for being non-derivable is what? Infinite slope. But yes, tangent should be there. So if tangent is there, this is what we call point of inflection. Am I clear? Point of inflection. Now, so what happens in second derivative test? Either the graph is like this or the graph is like this. It is minima, it is maxima. Here, second derivative is going to be positive. Here, second derivative is going to be negative because of their concavity. So what you do, first of all, you do f dash x equals to 0. Get the values of x. Now, at these values of x, you find second derivative. Now, at the values of x, you find second derivative. Now, if second derivative is less than 0, then fx will have maxima. See, second derivative is less than 0, function is having maximum. Second derivative is more than 0. And if second derivative is more than 0, function will have a minimum. Am I clear? So this is what we call second derivative test. And now sometimes, say at x equals to a, where first derivative was 0, second derivative is also 0. If second derivative is also getting 0, that means second derivative test has failed. Then the second derivative test fails and existence of maxima or minima will be decided on the first derivative test. Got it? So if the second derivative test is also second derivative is also getting 0, that means maxima or minima will be decided using the first derivative test. Am I clear? Now, let's take an example. Say fx is x square plus 1 upon x square. They are asking you for the maxima or minima of this function. All right. First of all, what will you do? First of all, we will find the first derivative. F dash x is 2x minus 2 upon x cube. Got it? Now what you will do? You will do f dash x equals to 0. So that means 2x equals to 2 upon x cube. That means x to the power 4 is 1. That means x square minus 1 to x square plus 1 is 0. Now, this cannot be 0 because it is x square plus 1. So, x square is 1. So, x is getting plus minus 1. Am I clear? Now, at these points, there is a possibility of maxima or minima. Now, how we are going to check it? We are going to check it using the second derivative test. Now, f double dash x is 2 minus minus, it will be positive 6 upon x to the power 4. Got it? Now, f double dash x add x equals to 1 is going to be positive, very much clear to everybody. And f double dash x add x equals to minus 1 is also going to be positive. That means x equals to 1. That means x equals to 1 and x equals to minus 1 both are points of minima. Now I have a question for every one of you, and whoever replies correctly will get a prize from me. The question is, if you remember in the beginning of this lecture, I have told you that the maxima and minima occurs alternatively, isn't it? For a function, maxima and minima occurs alternatively, means one maxima, minima, minima. But here in this case, there are only 2 points where maxima or minima can occur. But later on, I realize x equals to 1 is a point of minima as well as x equals to minus 1 is a point of minima. How can this happen? Anybody, switch on your mic and reply me. How is that possible that x equals to 1 and minus 1 both are points of minima? Tell me. Kaushik, if you would like to reply. How can 1 and minus 1 both be point of minima? Anybody? Vedant? You may reply in chat box if possible for you. See, basically what is happening, if you see the domain of this function is x belongs to r minus 0. So basically this function is discontinuous at x equals to 0. The theorem when I told you that was for a continuous function. If a function is continuous, their maxima and minima will occur alternatively. Here the graph of this function is like this. Like this. This is x equals to 1 and this is x equals to minus 1. And wherever, if you see, replacing x by minus x does not change the function. If I replace x by minus x, this function does not change. In our very first lecture, I told you what is an even function. So this is basically an even function. And if it is an even function, it is symmetric about y-axis. So however the behavior is there at x equals to 1, same kind of behavior will pursue at x equals to minus 1. So that is why this 1 and minus 1 both are points of minima. So this point is 1 comma 2. This point is minus 1 comma 2 because function is discontinuous at x equals to 0. It is not a continuous function. That is why we are getting two consecutive minimas. All right. Well, I would request to all of you to please practice from wherever the source you have at least few questions of maxima minima now. In our next lecture, we will talk about the word problems over it, like that cone is having a minimum area circle, rectangle is having a maximum area if the parameter is known. All right. So now I would like to ask your feedback over here, please.